Hey everybody, we're going to do a quick example here of one way we might use the normal distribution. So in this problem, I've set up here, I have a random variable W that's representing the birth weight in kilograms. This is taken from an actual study in the UK, I don't remember, some years ago. But anyway, so in some particular area, this was accurate at the time, and they found that the birth weights followed a normal distribution with a mean of 3.39. Remember, this is in kilograms, and a standard deviation of 0.55. And what I want to do in this problem is find the extreme 6% of birth weights. Okay, so first let me explain what I mean by that. I just mean the 6% that are furthest away. So those are going to be above some weight and below some weight. In this picture, so here's a picture of the situation. Here's a normal curve with the mean marked there at 3.39. What I'm looking for are two birth weights. I'll call this birth weight 1, or W1 and W2. And what I want is that the area above W2 is 0.03, and the area below W1 is also 0.03. So obviously there is 0.94 in between the two of them. Okay, so that's what I mean by the extreme 6% of birth weight. So when we're done with this, we'll say the extreme birth weights are above such and such kilograms and below such and such kilograms. Okay, so how are we going to do this? Here's the idea. We are going to go to the standard normal curve. So let's just sketch, I'll just sketch right below. It's hard to draw a straight line this low. We're going to go to the standard normal curve, and we're going to find two z-scores. I'll call it Z1, Z2, right? This is my standard normal with a mean of 1. And what I want to be true about these two z-scores is that above and below them, we have 0.03 data. In other words, area. In other words, Z1 is the z-score for W1. For W1, which, let's just write down the formula. How do we compute the z-score? Well, we take our data point, we subtract the mean, and we divide by the standard deviation, right? In other words, Z1 is equal to W1 minus the mean of 3.39 over 0.55. And similarly, Z2 is going to be equal to W2 minus 3.39 over 0.55. Okay. Now, this is not how we're going to find Z1 and Z2. We're going to find them with a normal distribution calculator because we don't have W1 and W2. But once we find Z1 and Z2, we can then go backwards to get W1 and W2. So remember what Z1 and Z2 are. They are z-scores with the area 0.03 above and below, respectively. So let's go to a z-score calculator. So I've got one here. All right, this is, I want the area. There's different ways we can do this. I'm going to say I want to have 0.06 outside, meaning I'm doing both at once. It's telling me what two values, what two z-scores leave 0.06 area on the outside of them. And that, of course, is going to be the ones we want because that's 0.03 above and 0.03 below, right? And notice what we get, negative 1.881 and 1.881. They should be symmetric. Just to confirm, we could do 0.03, let's say below. It just gives us the lower one, negative 1.881. And if we thought this through, we would know that it's going to be symmetric anyways. And so that would be a good enough way to get this. So let's write that down. Z1 we now have as negative 1.881, and Z2 we have as 1.881. All right, so now let's go back to our work. So remember what we wanted to do. We actually want to know the weights, not the z-scores, but now I have these two equations, right? So Z1 is equal to negative 1.881, which is equal to W1 minus 3.39 over 0.55. We multiply both sides by 0.55. And we add 3.39 to both sides. 3.39, I'll just write it this way, minus 1.881 times 0.55, and that's W1. We do exactly the same thing to this other equation, right, which is going to look precisely the same, except the 1.881 is positive. So we'll get 3.39 plus 1.881, 0.55 equals W2. So let's compute those two numbers really quick. I'll open up my like Desmos, and we'll just plug this in. Oops, let me scroll over to my numbers. So we've got 3.39 minus 1.881 times 0.55. And we have the same thing, except we're adding. So we get our two numbers. W1 is 2.3. Let's just go to 3 decimal places. Let's go to 2 decimal places. 2.36 is W1, and 4.42 is W2. Okay. These are both in kilograms. In other words, we could say the most extreme birth weights are below 2.36 kilograms and above 4.42 kilograms, right? Or the 3% of birth weights are below 2.36 kilograms and 3% are above 4.42 kilograms. Okay, so that's it. That's how we can go backwards from our z-scores to these, to the data values. There is a nice relationship in here that I just want to take a moment to generalize. Let's look at this z-score formula, right? We just worked with this a second ago. A z-score is the data point minus the mean over the standard deviation. If we do algebra on this, we end up with, right, let's write this one more time over here. X equals mu plus z times the standard deviation. Okay, this is just the same formula for z-score, but we've moved it around. But it gives us a way to think about the meaning of some of these things a little more clearly. Let's think about what we have here. This is our data point. Let's do this in a different color. Might be a little easier. This is our data point. Right? This is our starting point, the mean. So to find a data point, one way we can do it is start at the mean. What does a z-score tell us? One way to think about what a z-score tells us is a distance the data point is from the mean in units of standard deviations. Distance from mean in standard deviations, right? If you have a z-score of 1.7, it means you're 1.7 standard deviations above the mean. If you're a z-score of -7, it means you're 7 standard deviations below the mean, okay? So we find out how many standard deviations we are from the mean and in which direction, and we multiply that by the standard deviation, right? That means combined, these two things just give us the distance from the mean. So we start at the mean, add the distance from the mean, we land on our data point. And this distance also gives us the negative or positive. So it'll take us above or below, right? Which is what we saw here. This tells us how far below the mean W1 was. This told us how far above the mean W1 was. So in both cases, we just started at the mean and added or subtracted the distance to land on our data points, okay? And so this gives us a nice way to think about z-scores sometimes. Okay, that is it for this one. Thanks, everybody. I will see you next time.